All right. So this part of this lesson is about inverses, inverse functions. We've dealt with that before. It says previously we looked at inverse functions and finding the inverse of a given function, including exponential and logarithmic functions. We did that already. Now we'll look at finding inverses of exponential and logarithmic functions in general form. So not just parent functions, cute little b to the x or log base b of x, but really complicated a times b to the x plus h plus k. Okay, lots and lots of information here. So we can find the inverse of y equals f of x by determining the inverse operations to reverse the mapping. We know that if the coordinates are x, y on one function, the coordinates are y, x on the other. Everything is exactly backwards. We always find inverses by switching x and y and then solving for y. Okay, that's our process every time. We've done it a lot. We're doing that here. Switch x and y, solve for y, and then remember that we want to write it not as y equals, but as f inverse of x equals. That's what this last piece says. Write the final inverse function using correct notation. So that's going to show up like this, unless it's g, and then we do g inverse. Okay. So example 1 says, find the inverse of the function f of x equals 3 times 2 to the x plus 4 minus 15. Hopefully that's a little more clear on your paper. We're going to swap x and y. That's our first step. So instead of writing f of x, we're going to call it x is equal to 3 times 2 to the y plus 4 minus 15. Backing up just a second, I want to have a conversation with you about the function itself before we swapped x and y. What do you know about this function? Tell me transformations. Horizontally down. Vertically down 15.
Yeah.
Okay, vertically down 15. What else? Left 4. How do you know it went left 4? Because insiders lie. And that insider is x plus 4. So it went left 4. Last thing that you know from this.
It's vertically dilated by 3.
Vertically dilated by 3. Okay. Okay. So now let's find the inverse. We've got x is equal to 3 times 2 to the y plus 4 minus 15. What's the first thing we're going to do here? Add the 15 to both sides. Good. Okay, so 3 times 2 to the x plus 4, y plus 4, my bad. 3 times 2 to the y plus 4 is equal to x plus 15. Divide everything by 3. I agree. So now this is going to be 2 to the y plus 4 equal to x plus 15 over 3.
Can you write just two separate logarithms subtracting by each other so you put it open?
You could write it as separate logarithm. I wouldn't. You don't have to do that here.
Oh, okay.
Joseph said log it. Yes, because right now what I'm trying to solve for is y, and it's in the power. And we can't access that power without logging it. So the way this goes is 2 is the base. Log base 2 of the argument on the other side. So of x plus 15 over 3 is equal to, remember the log equals the exponent. So that y plus 4 is what the log is equal to. Last thing we're going to do here?
Subtract 4.
Subtract 4. So if we're writing this in all of its glory, we're going to have y equals log base 2 of x plus 15 all over 3 minus 4. And they want you to put it in inverse notation. So instead of saying y, you're going to say f inverse of x equals that stuff.
Where does the
Oh no, this is the cake part. Remember? I told you the first side is cake. We got this. The backside, we may have to call in the police or the helpers or somebody.
Who would that be?
Ready? Example 2.
I thought you were the police.
I am the police. Don't you ever believe anything different. Y'all ready for this? Find the inverse of g. So we're going to swap x and y, but this time it's logarithmic to begin with. So how do you think it's going to end up? Exponential. Yay. Okay, so we're going to have y instead of g of x, we're going to have x. I lied. X is equal to negative 3 log base 5 of y minus 4 plus 6. And we begin peeling back the layers around y. So what's our first move? X minus 6 equal to negative 3 log base 5 of y minus 4.
So be x plus.
Divide by the negative 3. Do y'all hear that? Are those the drums? No?
No, it sounded like chair or desks.
Maybe chairs are dead. Okay. I'm hoping it's not the drum line. I don't have time for a send-off.
I can tell the drum line.
Wait, would you raise it to the x plus 6 over 3?
Oh. So I have x minus 6 over negative 3 equal to log base 5 of y minus 4. So how do I handle getting into that y business?
You throw the argument into an exponent.
So it's base to the, right, the log equals the exponent. So it's base to this power equal to the argument. So 5 to the x minus 6 over negative 3 equal to y minus 4. Okay, everybody seeing that move? Because that's better. Yeah. Do you understand how we're converting from one to the other? We're taking the base to the power equals the argument.
Would it be smart to simplify
The x minus 3 business?
Yeah.
Shut up, Nikki.
Because
You could call it 5 to the, you would have it negative 1/3 x plus 2.
that just looks worse. Never mind.
Is it better? You like that better?
No.
Equals y minus 4? I mean, now we add 4 to both sides. You might be able to see actually what's happening better.
I agree with that, but like,
So you flipped it across the y-axis because it was a negative 1/3, dilated it by a factor of 3, shifted it left 2 and up 4.
so you can see it better, yes, but
Okay, so y equals 5 to the negative 1/3 times x plus 2 plus 4. Your final rewrite on that is going to be to call it g inverse. Nikki had the great idea of simplifying the fraction.
Yeah, but when we simplify it, like, if it's the 2, like, if we put it back in. I don't know, I'm lost. Because whenever I divide both these,
it's still
never mind, I don't know how we simplified it. That's just, I was fine before we simplified it.
My final answer here was 5 to the, I had x minus 6 over negative 3 plus 4.
I thought it would look better if you simplify it. My bad. My bad.
Where did the negative 1/3 come from? Is it
Well, I factored it out.
oh, and then
So on
after
this
that,
next one, do we
plus
write the
4
inverse
plus 4.
and set it equal to 1?
Say it again.
On this next one, do we write the inverse?
So if you y
I did that.
equals negative 1/3
So we do.
plus 2.
I did that. I'll talk to you about that in just a second.
Or we can plug in on it.
Can't you just?
I say we just ignore it and move on.
Yeah, I wouldn't.
Wait, so how do you plug in for that?
Huh?
Try to figure out how you plug in for
Are you on the next one?
Do you need a calculator?
No. Okay, so let's go on to letter C. Letter 3, number 3. Are y'all ready? Number 3. It says we've got this h of x function. Let k equal h inverse of x. For what values of k of x equals 1? So I'll tell you what I did. I found the inverse of h of x as my k of x sentence, right? Same as I did on example 1 and example 2. And then I set that equal to 1 and I solved for x. And I got the right answer. And then I thought, that's a really, really hard way of doing this. That's a Rube Goldberg method right there. Because if I know that x, h, and k are inverses of one another, and they're telling me k of x output is 1, then what do I know? H of x input is 1. So why don't I not find the inverse? Why don't I just plug in 1 into h of x? It's 3 to the x plus 1, so it's going to be 3 to the 1 plus 1 minus 2. H of 1 is 3 squared minus 2, or 9 minus 2, or h of 1 is 7. So what are all the x values where k of x equals 1?
7.
X equals 7.
I must have done something wrong.
X equals 7. When I don't know where it happened that they feel like that this is easier with logarithms, but read it. It says, it's actually much simpler when working with exponential and logarithm. Believe it or not, I don't know who they are, Passwater, but I don't think that it's easier here. It was hard. It was hard for me. Okay, so the first thing we have to do is we have to decide on a domain of this function. Okay, we know that our arguments must be greater than 0, right? We can't log a negative number. So on the second equation, that's pretty clear. X must be greater than negative 3. You with me? But on the first equation, this is a quadratic. Can you see that? So we must consider that this says x squared minus 4x plus 7 has got to be greater than 0. We're going to have to factor it to find those x values. Okay? Can't factor this one. It's awesome. There are not factors of 7 that make 4. So we quadratic formula. We sing the little song, x is equal to negative 4 plus or minus the square root of b squared minus 4
all over 2a.
AC all over 2a. And I want you to see what happens right here. Instead of a, it's 1. We have a positive minus 28. 16 minus 28. So what happens under that radical sign? It's a negative, which means it's imaginary. These are complex numbers, so this domain stuff doesn't matter. Okay, we get to throw it out. You're welcome. Okay, what does matter?
Whoa.
What does matter is x is greater than negative 3. It doesn't matter because it came out to be negative. Huh? Because you've got to consider it. You've got to consider it. We're trying to make a justification on the domain of this function. And what happened when we did the quadratic formula on this stuff, if you wanted to write it up here, you got imaginary numbers. So we don't worry. Cool? It is gross. Okay, so now we've got 2 logarithmic functions. They're being subtracted. So what we are to do is to set one of them, condense it. We're going to have log of, what's the base? 10. So we don't have log base anything. Log of x squared minus 4x plus 7 divided by x plus 3. We are interested in all the values of x for which f of x is greater than 0. So we're setting that log greater than 0. We're going to solve it. The first step to solving it is admitting it's a problem. No, is realizing what's the base here. What is the base? 10. Okay, so if I take 10 to the 0 power,
Get 1.
I get 1. So the argument here, x squared minus 4x plus 7 over x plus 3 is greater than 10 to the 0. You see how I went with that?
Yeah.
Or 10 to the 0 is what? 1. So you could just write, this has got to be greater than 1.
Multiply the front.
Multiply by the bottom. Those are gone.
You have to flip the infinite. No, that's just gonna be turn off.
So now we have x squared minus 4x plus 7 greater than x plus 3. Keep going.
Swing the 7.
Swing the 7. Swing the x, he means. Subtract the 3. It's quadratic. We want to set it equal to 0. X squared minus 5x plus 4 greater than 0. With 8. Factors of 4 that make negative 5.
5 and 1.
5 and 1.
No, 4 and 1.
Negative 4.
Negative 4.
X minus 4. X minus 1. That needs to be greater than 0. This is going to happen when x equals 4 and when x equals 1. Those are our points of interest. Y'all with me? So now it comes to creating our handy dandy sign chart. So draw yourself a sign chart. Notice that I did not put arrows on both ends of this here number line. Why?
Because they have to do that.
Has to go that way. Starting at negative 3. Because that's the domain of the function. This thing is chopped off over here on the far left. Negative 3 is as far left as it goes. And then our other points of interest are 1 and 4. Now, we're plugging in some values to our function right here, trying to see if it's positive or negative.
0.
0. Pick a number between negative 3 and 1. 0. 0. So what do we get? A negative times a negative?
Positive.
It's positive.
That'd be 2. 2 minus 4 is negative 2. 2 minus 1 is positive.
You wanted to pick a 2 between 1 and 4? He picked 2. 2 minus 4 is negative. 2 minus 1 is positive, so it came out negative. Something greater than 4? 5. I think we got a positive. So the intervals on which f is increasing, or f is greater than 0, f greater than 0, where? What's our final answer here? F of x greater than 0 on...
4 to infinity.
Okay, he says 4 to infinity, negative 3 to 1.
Oh, yeah, because it's 0.
Definitely not negative 3 to negative infinity. No, because it's not a closed bracket here. I'm going to attempt. Because at that point, it can't be both. It can't be both above 0 and at that point it equals 0. So if I'm saying when is it increasing or when is it greater than 0, not increasing, but when is the function greater than 0, I don't include the 0.
Oh, because it doesn't have the thingy.
Doesn't have the thingy, or equal to.
Right.
Or equal to. If it had the thingy, if this had said greater than or equal to, then we would close these brackets or close the parentheses. But it... Okay, let's go on.
We didn't learn that.
Example 5. Example 5, we have to start off with our domain. We can't even begin this function. What are all the values of x where g of x is less than h of x? We can't do that yet. because we don't even know where g of x and h of x are defined. I'm looking at h first because it looks easier. X has got to be less than negative 4. Would you agree with that? Not less than. Greater than. Gosh. This is going to be bad if I can't be straight with that. X is greater than negative 4.
Wait, how do we figure that out?
We say that the argument's got to be greater than 0. Argument's got to be positive. So x plus 4 must be greater than 0. Swing the 4. X has got to be greater than negative 4. The second thing that we know is x squared plus x minus 5 has got to be greater than 0. It's quadratic. It's not factorable. Enter the quadratic equation. Okay? And this one's not imaginary. I'll save you the time and space. You do actually have to do this one. So negative 1 plus or minus the square root 1 squared b squared minus 4 times a times c.
20. All over 2.
It's kind of creepy. Like it's like a little porcelain doll that sings songs very slowly.
From like The Exorcist.
It's bad. Okay, so these are our options. Negative 1 plus or minus the square root of 21 over 2. Both of these fall into the category where x is greater than negative 4. The other thing that you need to consider is that this was greater than 0. And when we did compound inequalities in Algebra 2, I taught you to read the sign where it says greater than as greater than. Greater than. So x is either less than the small one or greater than the larger one. Okay? So let's go in our calculator. Who has a calculator today? And you're going to be so quick with this. You're going to be so quick with this. On one side, I need you to get the positive option. Negative 1 plus square root 21 over 2. Negative 1 plus square root 21 over 2. Hey, y'all hang in there. Stay focused. Uh-huh. 1.79. Okay. And then negative 1 minus square root 21 over 2. Okay. If either one of these didn't fall into this category, we would throw it out. Both of them fit in that situation. Can you see that? Both of them fit as greater than negative 4. So how do we know what x is? We've got two different values for x. No, because it says greater, right? It says greater. But the rule on that is if given the option of 2, then you choose x is less than the small one. X is less than the small one. Or x is greater than the larger one. It makes an Oreo on the number line. I know y'all remember us doing this before. Where I shade on the outsides of the number line. If it was less than, I would shade in the middle. It would be an and, a sandwich. I know I taught you this. I think I did. Okay, well, all this does is this establishes our domain. This lets us begin to draw our number line. Which pretend like this example 6 isn't right here. And I'm just going to draw it down here underneath. We're going to come back and do example 6 in a minute. X has got to be greater than negative 4. That's the smallest piece of information that we can have. X must also be less than negative 2.79, but greater than positive 1.79. So what that means to me is X is not allowed to be here. There is no value in between on my number line that I'm able to be interested in.
So not supposed to be?
X is not those. X must be greater than 1.79 or X is less than negative 2.79. X is not allowed to be both. And also X can't go less than negative 4. Have we established our domain on this number line?
I think so.
Okay, now we're going to prove all the places where G is less than X. Okay? So now we go to work. And we set G of X less than H of X, which is to say the natural log of X squared plus X minus 5 has to be less than the natural log of X plus 4.
Hey, so that's what thing.
Why are we doing that now?
They have the same base, so what are we going to do?
Get rid of it.
Get rid of it? Sure. Set our arguments equal to one another or set our arguments less than one another. But we can drop the natural log business because they're both in the base E. Now what?
Move the X and 4.
Move the X, move the 4. Set it equal to or less than 0.
Doesn't the sign have to change here?
No, because we haven't divided by a negative. I lost my X's. I have X squared minus 9 is less than 0.
Hey,
It's a difference of squares.
it's 3.
X plus 3, X minus 3, less than 0. Those are our points of interest. We're checking places where X equals negative 3 and X equals positive 3. And good news, both of those fit in our domain that's allowed. That's fantastic. That's wonderful. So now pick a number between negative 4 and negative 3. Negative 3.5. Plug in right here. Negative 3.5 plus 3, that comes out negative. Negative 3.5 minus 3, that comes out negative. So overall, positive here. Pick a number between negative 2.79 and negative 3.
Negative 2.9.
Negative 2.9 plus 3, it's not enough. Minus 3, still negative. Nope, lies. The first one's positive. It's enough to get out of the hole. Negative 2.9 plus 3 gets us to positive. 2.9 plus 3 gets us to positive 0.1. Yeah, I know. This one's negative. We're not interested in between. Pick a number greater than 1.79, but less than 2.
2.
Or less than 3. 2. 2. So we get a positive and a negative. And then a number greater than 3.
4.
We get a...
Positive and positive.
Okay, so this one's overall positive. So our intervals on which G of X is less than H of X. Now, what we just found is where the difference is less than 0. So let's look at that. G of X minus H of X is less than 0. We need to find intervals where this is negative. That's going to be where G of X is less than H of X.
Negative 3 to negative 2, whatever that nonsense is, then y is to...
Negative 3 to negative 2.79. Or, not and, because it doesn't fit in both places. Or what else? 1.79 to 3. What am I doing? Why am I doing that? Sorry, lost my mind. That's a 2.79. No, we're doing the last one. What are y'all thinking? We got 12 minutes, and there's a example 6.
Hold on. Where did you get your greater than?
The last one's easy.
Less than.
Hang in there. Where did I get my what?
Yeah, you said natural log x squared plus x minus 5 is less than natural log of x plus 5.
Because they said set G of X less than H of X.
Okay. Now,
So I took G of X and I set it less than H of
You
X.
said it had to be less than 0. Where did that come from?
So I subtracted H of X from both sides. So G of X minus H of X must be less than 0. That's how I read my sign chart. I'm looking for negatives on my sign chart, negative intervals.
Which one's your sign chart is your line?
The line. That's called a sign chart. And how do you set up the sign chart? You have to look at the domain. It's a lot. It's a lot. We will have a work day tomorrow. Hey, everybody hear me. We're going to finish example 6 right now. We will definitely have a work day on this tomorrow. So we are working worksheet C. If I were you, I would do the front. I really think you can handle the front. I would definitely save the back for tomorrow. Okay? We are about to do example 6, so in no way are we free to go at this moment. We are doing it. Because y'all are champions. You're champions. It's about to happen. Okay, here we go. Example 6. Are y'all ready? It's not nearly the same business. 1, the domain business is not necessary. Why? No. Why do I not care about the domain? It's exponential. What's the domain on an exponential function? All real numbers. Hallelujah, amen. All real numbers, because on a logarithm, we can't go less than 0. Can't log a number less than 0. But an exponential doesn't have that problem. Exponentials are asymptotic on the x-axis, not on the y-axis. So the domain on an exponential, no restrictions, all real numbers. Okay? That's the first piece of good news. K of x is exponential. The only piece, no, it's good. This is good. What are all the values of x for which k of x is less than or equal to negative 31? Set it equal to negative 31. So we've got k of x, our function, 1 minus 4 times 2 to the x minus 3. That's going to be less than or equal to negative 31. And what?
Log it.
No, not yet.
You gotta subtract.
Just solve it. Subtract 1. Negative 4 times 2 to the x minus 3. It's greater than or less than or equal to negative 32. What are you doing? Divide by negative 4. Flip the sign. 2 to the x minus 3 is greater than or equal to 8.
Oh, yeah, you gotta flip it.
Flip the sign. Now, yesterday we looked at this. We said, how do I solve exponentials when they're in different bases? Oh, what if I rewrite them as being in the same base? Base 2. So I'm going to keep this one, 2 to the x minus 3. But I'm going to rewrite 8 as what?
2/3. 2 to the 3.
2 to the 3rd power.
Yeah.
2 cubed. Now if my bases are equal, my powers are equal. You were going there, right? That was what that face was. You were about to say it. It's on the tip of your tongue. If my bases are equal, my powers are equal. Check it out. 2 to the x minus 3 equals 2 cubed. X minus 3 is greater than or equal to 3. X is greater than or equal to 6. That's it. K is less than or equal to negative 31 when x is greater than or equal to 6. Okay, tomorrow we attack worksheet C. I'd love for you to do the front before then.
I'll think about it.